Next. Okay. So yeah, so we just did, I showed you some brief vignettes, let's say, of the first detection and a brief thing about the binary black holes. So now let me go to a different problem altogether. So this is entirely different from binary black holes. And these signals are probably not so well known outside the people, group of people who do this. But these might well be the next set of detections that we find. And so let me describe that for you now. So the scenario is, imagine a neutron star, this other mechanism, but just imagine a neutron star, which is slightly deformed from axisymmetry. So imagine a neutron star with a small mountain on it. So just like the Earth here, Mount Everest, the highest mountain. So imagine a neutron star with some deformations on its surface. Okay. So then you can define this quantity here, which I'll call epsilon, which is sort of a measure of the asymmetry of this neutron star. So this is, if I imagine the principal moment of inertia of this object, let's call them I1, I2, and I. So I is along the z-axis. These are the x and the y-axis. So then this one is a measure of the asymmetry of the star. So I1 minus I2 divided by I. And then you apply the quadrupole formula that you heard about in Scott's talk in the morning. And then what you'll find is this emission of this gravitational wave, so in which the amplitudes A plus and A cross are constants, and they depend upon a dimensionless number h naught and these angles. So if I can draw the picture here, so imagine a neutron star which is spinning around its axis, which has a slight asymmetry in it. And our detector is somewhere along this direction, and this angle is iota. Then the wave that is seen is of this form. So A plus and A cross depend upon this quantity h naught, which in turn depends upon epsilon, this quantity here, to the distance to the detector, that is the distance in this direction, and upon the rotational frequency, that's nu. Okay? And this angle iota tells you the polarization of the wave. So if you are exactly sort of along the axis, then you get the largest amplitude. If you are in this direction, then you get the smallest amplitude. And again, if you are in this direction, what you see is a circularly polarized wave. If you're in this direction, you see a linearly polarized wave. That's the ratio of A plus and A cross. Okay? So when cos theta is 1, then this is the same as that. So it's circularly polarized. If cos theta is 0, that's on the plane. This is 0, and that is some non-zero number. Anywhere in between, you get elliptically polarized signals. Okay? So it's a very simple model. And the phase here is just the rotational phase of the neutron star. And a measurement of such a signal will tell us how deformed a neutron star can be. Okay? There's other mechanisms to produce these signals. I just mentioned one, which was this thing about a deformed neutron star. There's other possibilities which involve sort of fluid modes in the neutron star or other exotic effects. But this is the canonical sort of model. So let's just go with that for the moment. So the first thing to note is that the values for epsilon are very uncertain. So we don't really know how deformed a neutron star can be. It is possible that neutron stars are extremely symmetric, and the value for epsilon for real neutron stars is absolutely tiny. It could be 10 to the minus 10 or something. It's possible. We just don't know. Okay? So there's some estimates for what it could be. So just before that, just to give an idea for what this would tell you about the neutron star, let's do this little thought experiment. We know that Mount Everest is about 9 kilometers high. Why is it 9 kilometers? Why could it not be 20 kilometers?
It is on Mars.
Exactly, but why on Earth can it not be 20 kilometers? Right, so it's, if I imagine this is Earth, this is, let's say, Mount Everest, this is the height. The pressure at the base of Mount Everest is going to be density of that rock times 9.8 meter per second square times the height. If this pressure is bigger than the pressure that rocks can sustain, then the mountain cannot be higher than that. So just the stuff that makes up the crust of the Earth, that determines the highest possible mountain that can be on a planet. Of course, if for the gas like Jupiter, it's a different situation, but for the planets made of rock, this is the thing that you would do. So since you mentioned Mars, you can do a short exercise there. So you can say on Earth, we have Mount Everest is 9 kilometers, and G is 9.8 meter per second square. On Mars, we know that the highest mountain, does anyone know that? It's 22 kilometers. And G on Mars is, you can somehow remember this number, so it's 3.7 meter per second square. So now, let's say we didn't know this. And I want to sort of know, before even looking at Mars, what is possibly the largest mountain on Mars? Let's use this simple model here. Assume that Mars has same kind of rock like on Earth. So then I just do 9 kilometers times 9.8 divided by 3.7. Can someone do that for me? 23.8. And the highest mountain is 22 kilometers. So it's
Like to Venus, where it is Earth size, but mountains still seems.
good question. I don't know, but somebody can look up the numbers. I just remember the number for Mars. I don't remember it for the others. But this sort of tells you that this very simple argument gives you an estimate for how deformed a planet can be. And the same thing with neutron stars. So if you would know what the largest value for epsilon is for a neutron star, then we know something about the crust of a neutron star. Yes?
Should be also related to the height of the atmosphere, starting of the atmosphere.
Indeed, yes. I mean, that's going to be a smaller effect. But yes, if you were to do the full calculation, yes. But I would guess that's a very small effect.
No, I just try to mention the starting of the atmosphere, if I'm not wrong, 11 kilometers or something like that.
Right, but the density is much lesser, right? So it's just air. So that's much less dense than rock. So that should be a much smaller effect.
Yeah, you're right, but I try to say, I mean, it could be like maybe 15 kilometers, of course, just because it should be higher than the starting of the atmosphere.
Oh, but that can be, right? So let's say that Mars, I don't know the atmospheric conditions of Mars, but I would guess that Mars is of course, a much thinner atmosphere, and the mountain is much higher. So I guess for Mars, it does extend beyond the atmosphere. But I don't know. I mean, that's something that can be checked. Right, but going back to neutron stars, we know the neutron star crust is a lattice. So then if you were to know how much you can deform a neutron star crust, that gives you the limit on epsilon. And therefore, if you can measure this epsilon from gravitational waves, so this means that you would have to sort of observe a neutron star with a telescope and in gravitational waves, and combine these two, then you get the value for epsilon, then you know something about the crust of a neutron star. And that is not something you can measure in a lab so easily, right? So the potential of these observations is really great. So, but this is a very difficult problem, and I hope to explain in these remaining 40 minutes why. Right, so first of all that, there's a value for the maximum ellipticity, so there's different estimates for what it could be. But again, just because a neutron star can sustain a mountain of a given ellipticity, it does not mean that in its history, things have happened that would cause the mountains to be formed in the first place, right? So on Earth we have plate tectonics, which is what causes the mountains, but it's possible that planets may not have plate tectonics, right? Maybe it's a different situation in certain planets. So then the mountains would simply not form. But again, so if you observe this independently, then you can answer these kinds of questions for neutron stars. So now let's explain why is this problem difficult. So I described to you the signal. This is very, very simple. Okay? So if I'm in the frame of the neutron star, I just have a constant amplitude, and the phase, which is the simplest possible thing you could imagine, the phase is simply 2 pi f times t plus, let's say, frequency derivative times t square, and so on. Okay? So if we ignore the spin down, it's simply a constant rotational frequency. That's it. So how in the hell can this be difficult? So now if you had a detector on the sun, that would be fine. Assume neutron star is at rest with respect to the sun, or at least at a constant velocity. So on the sun, you would see the same phase. So if the detector can survive being on the center of the sun, then you're good. You get a signal, which is a pure sinusoid, and that's easy to find. However, the problem is that the Earth is moving in its orbit and around its axis. So that means, even though in the phase, in the frame of the star, the phase is as simple as this, it's just some frequency and a small corrections from frequency derivatives. If you want to go to a detector, then and you want to find the arrival times of the crest of the wave on the detector, then you got to correct for the motion of the detector. So this thing here, r dot n, so r is the position of the detector in the solar system frame, and n is the direction to the star. So this extra term tells you the difference in the arrival time of the wave from the solar system barycenter and on the Earth. And this difference depends on the sky location. In principle, this is also true for the binary black hole detections that I told you about. So it is true that, in fact, this is what explains the delay of the signal from Livingston to Hanford. However, since those signals are so short, a fraction of a second, the detector position is really a constant in that duration. So for these very transient events, this time delay is just a constant shift. That's it. But if I have an instrument that is really, and I have to observe this thing for several weeks or months, this R is changing in a complicated way. And so sometimes the signal arrives first in Hanford, then Livingston, sometime later, first in Livingston, then in Hanford, and all possible combinations. Okay? And moreover, if the pulsar were in a binary system, which is a very important case, so this is not the signal from the orbital motion of the binary, but a spinning neutron star which happens to be moving in a binary system. Okay? So in this case, you then have to correct also for the delay of the waves in the binary system itself. So this RP is the position of the neutron star in its binary system, in its binary orbit. And of course, on top of this, you got to add relativistic correction. This is not really important, but they are there. So the Shapiro and the Romer time delays and so on. That's the Romer time delays, Shapiro and Einstein time delays. So in the end, the phase, the simple one, if you convert it to detector time, becomes a complicated thing. Then the phase depends on the position of the source, for example. For a binary black hole, the position of the neutrons of the system does not enter the phase itself. That's a constant shift. But in this case, because of this effect here, the position to the sky position becomes something that you have to search for, and it enters the phase of the signal. And this is what I said, is just a Doppler shift calculation. Okay? So the frequency is the derivative of the phase. So if you just do this translation of the times, then you get this expression here for the observed frequency versus the intrinsic frequency of the signal. depending on the velocity of the detector, the observed frequency can be modulated, or will be modulated, in fact. Okay. And what does V consist of? Assume the star is isolated, so no orbital motion. Then the Earth can move in its orbit or on its axis. So for the rotation of the Earth on its axis, V over C is about 10 to the minus 6. For the motion in the orbit, V over C is 10 to the minus 4. Of course, this depends on the latitude of the detector. So for LIGO and for and so on, it's about 10 to the minus 6. So if you had something on the North Pole, that would be, of course, different. But this one is independent. This is just the motion of the Earth in its orbit, 10 to the minus 4. So that means that if I have a signal at 100 hertz, the shift in the frequency is about 100 times 10 to the minus 4. That's about 10 millihertz. It's a small amount, but it makes a big difference. If I look at something at 1,000 hertz, at a kilohertz, so 1,000 times that, that's 0.1 hertz. Okay? So these can be large effects that have to be taken into account. So just to now count the parameters of the signal. So first of all, you have the parameters which I'm calling amplitude parameters. I'll explain tomorrow why precisely. So these are these quantities here, which is the inclination angle to the system, cosine of the inclination angle, initial phase, this angle psi that's got the polarization angle that Scott talked about, which tells you the other angle of the orientation of the star, and this constant amplitude here. So these do not enter in the phase. And then you have the parameters which change the phase of the system. So phi appears in the phase, but doesn't change the phase evolution of the system. That's what it means. So these are what are called the Doppler parameter. These sort of modify the phase of the signal. So this includes the frequency derivatives, the high derivatives, and so on, and the sky location. And then in addition, if the star happens to be in a binary system, then you got the binary parameters as well. So if it's circular orbit, then you got the period, some time of the ascending node, that's a particular time in the orbit to set the phase, and also inclination of the orbit itself, and the, of course, semi-major axis of the orbit. It appears in this combination, a times sine of that angle. So then you have 3 parameters appearing here. And if the orbit is eccentric, then you have 2 more. Why? Eccentricity and which direction the orbit is oriented in. That's all. So in the full case, you have 5 parameters appearing here. These many appearing just for the frequency evolution. And in addition, these parameters, which in fact are not that difficult, but still they appear in the waveform model. Okay? So what this means is that you got to then search over all of these parameters here, and this is very, very difficult. And this is in fact by far the most difficult computational problem in gravitational waves. By far more than anything for binary black holes and neutron stars, by far. So this means that these problems are limited computationally. So we cannot do a full match filter search for these signals. Okay? So a lot of the effort in this problem here goes into dealing with this computational problem. We got a very large parameter space, a very weak signal. So we have to look at a lot of data to get the signal, but that becomes very, very difficult computationally. So to get into this game, you really need a big computer. So let me just talk a little bit more about the frequency evolution. So imagine now that you have not emission by gravitational waves, but emission by magnetic dipole breaking. Okay? So imagine a neutron star by itself with a magnetic dipole, which is misaligned with the orbital with the rotation axis. So again, you have a neutron star. This is the rotation axis. And let's assume this is then the magnetic dipole axis. and that is spinning around the neutron star. Okay? Again, going back to your E&M calculations, you can convince yourself that the magnetic dipole breaking gives you this evolution for the frequency depending on the radius, the magnetic field, and moment of inertia. So the rate of frequency change depends upon the cube of the frequency. And this angle alpha is a misalignment between the dipole and the rotation axis. Okay? So of course, if alpha is 0, then there is no loss in dipole radiation. But if alpha is more misaligned, then we get a larger breaking radiation. Okay. Now the same thing happens for gravitational waves, except it's not a cube, but the fifth power. So in general, if I have a neutron star which has both emission due to this dipole radiation and also because of gravitational wave emission, then in general we get an expression of this kind for nu dot. And now the actual emitted amplitude then depends on these combination of parameters, on the magnetic field, the radius, moment of inertia, and of course on the ellipticity as well. That determines this K5. Okay? So this is the canonical model that you should keep in mind. Right? So now let's try to search for systems of this kind. So now there's three categories of systems. So there's of course the known pulsars. So we have the famous pulsars like the Crab or Vela. So for these ones, we know the star location, we know the frequency derivatives, so we know precisely the template we should include in the gravitational wave search. You might allow some small variations, but still, you more or less know exactly the point in parameter space that you want to target. And these are very easy. So this you can do on your laptop with some effort, but these are really easy. But as I'll show the results, but so far we haven't found any signal from these kinds of searches. So then you want to try a bit more. You want to say, well, let's look for more interesting objects. Objects, for example, in supernova remnants, right? We might have a supernova with a young neutron star, which is highly deformed. So we have a supernova, we know the star location, but we don't know the frequency of the star. So these are the directed searches. So in this case, you know the star location, but you do not know the frequency, you do not know the frequency derivatives, and so on. And these already, as I'll describe later, these are limited computationally. Because the frequency range could be 1 kilohertz that you have to search. Right? So a good example is Vela Junior, that's 800 years old, about 300 parsecs away, but we don't know the frequency. Or you might imagine sort of regions with lots of young neutron stars, the galactic center, so other star-forming regions. So then you know roughly the star location, but again, you don't know the frequency. And then the most difficult ones, let's say you know nothing, the blind searches. Then you hope that there's a neutron star that's very nearby that has somehow been missed by any telescopes. It's possible. I mean, I'm not saying it's likely, but it's possible. So in that case, you've got to search over the whole sky and over frequency and spin down and so on. And these are the most difficult searches.
Excuse me, this Vela Junior, is it the known Vela pulsar, which also emits gamma rays at 89 milliseconds?
No, it's not that one, no. This is Vela Junior, we don't know the frequency. So Vela is a different one. Vela Junior is different. Okay? And again, the important point, except for this simple case, for the known pulsars, all the others are limited computationally. So sadly, then, to find how high a mountain can be a neutron star, we really have to spend a lot of effort in this computation problem. So, but we can do one thing. We can estimate what is the largest possible amplitude that we can get from a neutron star of this kind. How could we do that? Well, it's easy. We actually have an expression for the energy loss in gravitational waves. It's again the expression that Scott had. So E going like h dot squared. Did you have that actually? Yeah. So indeed. So you had E, which goes like the square of h plus and h cross. You just integrate over a whole sphere, large sphere surrounding the system. You average over a few cycles, and you get the rate of energy loss from the neutron star. And then this must balance. If this is the only energy that is lost, if I ignore the dipole radiation completely, then this must balance the rotational spin down on the star. And I combine these two, and I get a limit on the amplitude, which looks like this. It goes inverse to the distance, and it is proportional to how the moment of inertia and how fast the star is spinning down. So for any star for which we know frequency and f dot and the distance, we can compute this limit. This is called the spin down limit for the amplitude. So then a useful figure of merit is that for the known pulsars, how close do we get, or can we beat this limit, in fact? Because if we are below this limit, then it's not interesting. Then astronomers will say, well, you didn't expect to find anything anyway. But if you sort of beat this by a large amount, then things get interesting after that. And in fact, this is the result from the LIGO collaboration. This is from earlier this year. So let me go through this slowly. So these are all the known pulsars that they've targeted, all these dots, all these stars and everything. For each star, which is the observational, this is the limit on h naught, that is the quantity that I was telling you about. This is the frequency, so it ranges from, this is 100 hertz, 1,000 hertz, this is about 10 hertz, I believe. These stars are the upper limits on the amplitude on this h naught quantity, and the corresponding limit on the spin down due to the spin down argument are these triangles. Okay. So for almost all the neutron stars, the spin down limit is below what we can actually find. So for these stars, we don't expect to detect them, and we don't. We can just set a limit on the amplitude, but it's not that interesting. But there are these systems here. The Vela is a very important one, and the Crab is a very important one. For these, the limit is above what we can find. In other words, we can constrain the amplitude to be much less than this limit that I just calculated. And then you can estimate what fraction of the energy loss could be possibly in gravitational waves. Okay? And the Crab is sort of the star of this calculation, and the Vela is also a very interesting one. And there's a few other interesting pulsars, but these are sort of the really important ones. So for the Crab, we can limit E dot to less than this %. So this is very interesting. The fact that we still haven't found a signal from the Crab is an interesting fact. It tells us that the mountains on the Crab can be no more than 3 centimeters in height. And it's remarkable, right? I mean, imagine this system this far away, we can constrain the mountains to 3 centimeters. And Vela is okay. It's also impressive, but not as much as the Crab. Okay. So now let's go to a more complicated system, which is my favorite, in fact, in this business, but also a very difficult one. So now you might ask the question, well, we have these neutron stars. You can say, why should they be deformed at all? What causes them to be deformed? A star left by itself, out with nobody to interact with, probably over time the mountain will all relax and it'll become perfectly symmetric. That's probably the likely fate of a neutron star. The one exception would be if there is stuff falling on the neutron star that is accreting, so that is causing mountains to be formed, and then things are more interesting, then you have a chance that you might detect something in this way. So it's a very nice source for this, which is called Scorpius X1. So this is what's called X-ray binary. So this is at 2.8 kiloparsecs. So this is a neutron star with a companion that's 0.4 solar masses, which is accreting matter on the neutron star. and its orbital period is about 19 days. The problem is that we don't know the spin frequency of the star, of the neutron star. This is the brightest X-ray source outside the solar system that we know. It's a beautiful candidate. If we knew the frequency, this would be great, but we don't. We know the orbit reasonably well, but the frequency is the big problem. So now there's a nice argument, which goes back to Bilston and Wagner before that, which is you might have a scenario in which you have stuff falling on the neutron star that is spinning it up, and this emission of gravitational wave that is spinning it down. They could balance between these two effects. Okay? And say, well, why is it interesting? So the reason it's interesting is for the following observation. You look at all occurring neutron stars in the universe that we know, for which we have a spin frequency measurement. Okay? And then you say, how fast are they spinning? The fastest one is at about 700 hertz. It is very fast, but from what we know about neutron stars, they could spin a lot faster. They could spin at more than 1 kilohertz. So from all what we know about neutron stars, from the crust and so on, if they spin really fast, of course, the centrifugal forces will break up the crust of the star, but that's going to be more than 1 kilohertz. So the question is, why do neutron stars not, observed one, not spin that fast? Why is there a gap between the fastest known spinning neutron star and the actual limit that we know on the spin? And the reason could be precisely this balance, which is that there's this mechanism which is spinning the star down, which is gravitational waves, and that could be the one causing this discrepancy to occur. So for all the arguments for what is the actual amplitude of a wave from a neutron star, this is probably the strongest one. So let's try to get this limit that Bilston got back in '98. It's actually a very easy calculation. The result looks like this, which is that the amplitude that is h naught squared is proportional to the flux of X-rays that we get from the neutron star divided by the spin frequency. How do we get that? Well, it's easy. It's a very basic calculation, it's an approximate calculation, of course. So the assumption is that the stuff falling on the neutron star causes the star to spin up. So we got to find the torque by the stuff that is falling on the neutron star and balance it with the torque that would be because of the gravitational wave that is leaving the system. Okay? So the torque due to gravitational waves is just rate of energy lost by frequency, and just get this number. The accretion torque depends on the mass accretion rate, which in turn determines the luminosity of the X-ray that we are getting. So this is the link between the observed X-ray luminosity and the accretion torque. So we get this expression here. You put it all together, you get the mass accretion rate depends on the X-ray flux in this way. F is the X-ray flux. And then again, put it all together, you get the little bit value, you get this expression here. So the amplitude depends upon inverse of the frequency to a square root and upon this X-ray flux that is measured. So for a given low mass X-ray binary, if you just know the flux, you can get this number here. Assume canonical values for the radius and mass of a neutron star. And if you know the frequency, then that tells you what this h naught is. Of course, you don't know what the inclination angle is of the star, so there's some uncertainty built into that. But apart from that, this is the answer. So for a given system, if you can beat this limit, then you're in business. Then you can either rule out this balance scenario, or this tells you something very interesting about it. And this, to my mind, is a bit different from the spin non-limit. The spin non-limit is a very unrealistic one, right? Nobody would believe that there would be zero emission in the dipole part. In this case, this is a realistic thing. I haven't gotten magnetic fields into this yet, but you can include magnetic fields and repeat the calculation. It's more complicated, but you get a similar limit at the end of the day. Yep.
The neutron star's medium is vacuum for this calculation. If it is plasma, if you consider the accelerating particles around the neutron star, then this calculation will change.
Well, not really, right? So I mean, you can, of course, the true model, let me just describe this since you mentioned it, right? So the actual model is this, right, which I haven't included here, but you can do the calculation. You get this dipole field, so you get these field lines around the neutron star. Right, so let me choose a different color for that. Right, so you get this dipole field here. Then you got an accretion disk that will be in this plane. It's an accretion disk, and the accretion matter that falls up to here, then it follows the field lines, and matter accretes along the poles. Okay. So in fact, you do include the matter, all the plasma in the accretion disk, and that is going to sort of fall in, follow magnetic fields, and follow neutron star. And you can repeat this calculation in this more accurate model, and you would get a similar answer. It includes no extra parameters, which I'm not going to go into here, but you can do the calculation for that as well.
The extra parameter presumably is a misalignment of the dipole.
It's a misalignment. There's also the magnetic field value itself. That sets the radius at which the field takes over, dominating the kinetic flow of the accretion. But everything you can do in this simplified model. But you do include sort of matter effects, not just a vacuum thing around the star.
But for low mass X-ray boundaries, the magnetic field is very low compared to normal.
Exactly. So
it's hard to channel in general for magnetics.
exactly. That's why in this I did not include a magnetic field. I'm just saying if you want to include it, you can also do that. So indeed, it is a small effect as we expect for low mass X-ray binaries, but so that's why this is reasonably accurate, I think. And that is why if we were to beat this limit, it would be very interesting. So let me show you the best current limit on these kinds of searches. So this is against Scorpius X1, our favorite candidate. And this is the spin down limit. This dashed line is that limit that I just talked about. And this shaded line tells you the uncertainties given this inclination angle to the system that we don't know, of course. And the best limit is this one. So we're getting very, very close to beating the spin down limit. And this was back from 01 data. Okay? So ignore these other, these are not good enough, so forget about those. This is the only one to think about here. So this is based on something that I was involved in still am. This is based on a cross correlation of data between Hanford and Livingston, and you can really get very, very close to this limit here. And presently we have analysis for O2 that will beat this torque balance scenario. So in the next few weeks or a few months, not weeks, but months, I would say, you're going to get limits which are better than the torque balance for SCO-X1. And maybe a detection, right? Of course, if you beat the limit here, the frequency may be somewhere else, so then it's not really, you don't really rule out the scenario, but still it tells you something interesting. Okay?
In case of pseudo pulsars, like Vega and Crab, these observed glitches which makes them to change in frequency.
Indeed.
In that sense, I mean, these mountains on these things, they should be comparable to those theoretical explanations of glitches.
Indeed, yes. So what is done in practice for these systems is that you have a glitch time. You look at the data before and after the glitch separately. So you don't include the glitch in the full phase evolution of the signal. Of course, you might say that, well, for the unknown neutron stars, we're not including glitch in our model. Could we miss a system because of that? And that is true. So we could. So in that case, we do have to improve the models to include a glitch in all the searches that we do. But the mountains itself would roughly be the same before after the glitch. The phase evolution would have a break in that case.
I mean, does that mean that those mountains, like 20 centimeter on Vela, could really create gravitational waves which can be detected, or is it conclusion?
Yeah, well, so far we haven't found anything, but in principle they could, yes.
Okay. Okay, I mean, we have to wait another glitch or so.
Well, there's a different thing you could try. You could try to search just at the glitch. If you observe, you can resolve a glitch in time, you could search for a pulsar exactly at the glitch. That is possible. And there might be interesting effects you could see there, but the problem is that it's a very, very short time that the glitch would happen in compared to the full, month and year-long observation. So intrinsically, it's a more difficult thing to try. And you don't know exactly how the phase will behave during the glitch, so that's a complicated thing. So it's 4 o'clock, so I should stop now, I think.
Questions?
But indeed, yes. So I was going to stop, and then I'll continue on this tomorrow, and you can ask questions for the moment.
Thermonuclear bursts are assumed to be due to the accumulation of the matter on neutron stars.
That's right,
So
yeah.
have you checked out those kind of mountains?
Yeah, so you can do this search, which we actually did back about 10 years ago. So all the accreting neutron stars, you have different classes. You have the burst ones, for which you get this burst oscillations, and from that you can measure the spin frequency. And from that you might hope, given the flux, how large can amplitudes be for that. You can compare that to the low mass X-ray binaries, for which we don't have a good model for the spin frequency. And you can also look at the millisecond pulsars, which you frequency very, very precisely. But it's a conspiracy of nature, which is that the ones for which you know the frequency the best are the least luminous in X-rays. And the ones for which you know frequency the least are the most luminous. And the most luminous means the most amount of infalling matter. So it's a conspiracy. So I mean, I don't know how to, but we did the study, in fact, and still Scorpius X1 was the most promising case. Yeah.
So you said the continuous phase searches are limited by competition. Is it also true for the CBC searches?
No, it's not true for those. So for those, I'm not saying it's an easy problem, but with existing resources, it's easy to apply what I mean is the following. Based on the signal model, you have an optimal method for doing the search, which is a full match filter. I'll explain that in the next lectures. But you can do the optimal search, and you can scan all the data in the full parameter space. And that can be done with some effort, but it can be done. For these signals, you know what the optimal method is, you just can't apply it to the actual data and for the full parameter space. So the CBC ones are not limited in that sense, but these ones are.
And what are the differences between similar CBC searches, like ICD searches, one with it?
So those are all similar. So in fact, all the CBC searches, with some variations of what you do, they're essentially similar. So they are all match filter search in some way, with some VROs applied to take care of actual data problems, and some template bank construction. I'll explain all of that in the next lectures, but those are all more or less the same, because you know what the right method is in that case. The difference are in the details in that situation. In this case, you do not know what the optimal method is, given the limited on computation.
Any other questions,